It should be possible with a 6-page paper.
No, but the 6-page paper is also supposed to be heavily reliant on the sunflower.
That's what I was going to say. It probably relies on heavy stuff,
Yeah.
even though it's short.
I find it very funny. It's like I just read the article in Avanta magazine. Like,
They say that the scariest type of paper is the paper where the references occupy more pages than the paper itself.
Sorry,
It's the
just-
scariest type of paper.
My office.
You find one of those, you just run away because
English for us, good.
Yeah,
But then not talking about that in specific.
yeah.
Everybody is here. Question that never has an answer. All right, good. So Leo will try to teach us about association schemes and codes.
I just put a timer so that I don't lose track of time. Because last time I completely forgot to take breaks, so I'll try to take a break this time at some point. So yeah, association schemes.
Remind you if you need.
Yes, if you can remind me, that would be nice. But okay, so association schemes and codes. So the idea here is I'm going to cover kind of the basics of the association schemes in this lecture that hopefully by the end you will see that there's much more structure to the Hamming cube than what we are probably used to. Normally we just see as the Hamming cube as saying, okay, you want to send some sort of message and it's going to be encoded by bits, but you want it to be robust to failure, right? So robust to noise. So instead of using all possible code words, you just take some subset to the end and you call that your code. And you're interested in two quantities, right? So first you want this to be large so that you can encode a lot of information. And on the other hand, you also want the distance of the code to be large. So what is the distance? Is just the minimum x, y, and z, x and y of the distance x, y. So here's the Hamming distance. Oh, yes.
That's okay.
Yeah, okay. Hamming distance, and you want this to be large. And the reason is because, well, at least if you ignore from the algorithmic perspective, you send a message, and then if there's corruption by strictly less than distance over 2, a priori, if you know the code, you could just look at the nearest code word and you retrieve the message, right? So now, I'm not going to get into details too much about the algorithmic part of this, but we're interested in just from the existence perspective, right? How large can you make the size of the code while the distance is still large, right? So the classic results are by Gilbert and Varshamov. This is in the 50s. And what they say is that, taking random linear codes is good. So it's not going to be too important for us how good it is, but they give this lower bound. You just take a random linear code. Okay, granted, Gilbert just takes a random code, and Varshamov proved that random linear codes are good. Good in a certain sense. It doesn't matter too much what are the bounds for us now.
What does it mean? Random?
You pick uniformly at random, and then you want a certain
subspace uniformly at random.
Yes, yeah. So Gilbert just does not the subspace. Is just pick words uniformly at random, and if you pick with a certain probability each word to be, and you just change your parameter p, you're going to see that there's a good trade-off between distance and the size. Varshamov said, well, actually, if you want a linear code, you could pick a generating matrix for this linear code uniformly at random. And if you set up the number of rows appropriately, you're going to get a good distance trade-off with the size of the code, with the rank of the matrix. But it's not too important here. We're going to be more focused on the upper bound, which is due to McEliece, and not even the upper bound itself, but the technique to get to the upper bound. So McEliece, Rodemich, Welch. So this is from the 70s. And what they did is you get an upper bound from analyzing
Upper bound on the side of C.
Yeah.
Like, yeah.
upper bound on given analyzing Delsarte LP. So the objective of this talk is to explain what is this Delsarte LP. I'm not even going to actually retrieve this proof because the analysis is kind of messy and somewhat technical and is not going to be really important for our result. But I will retrieve why is it that you get an upper bound, right? There is a structure on the space, right? Instead of just seeing it as a hanging cube, we're going to see it as what are called these association schemes. And every time you have an association scheme, you have an associated Delsarte linear program that gives you upper bounds over codes of this scheme. Okay, is that clear?
Or those who want to see actually the proof of this, not their proof, but it's about this.
Yes, there's
Fernando gave a lecture about this in the
yes.
talk with all detail.
Yes, exactly, and there's a more modern proof that is Sermondiski, and it is essentially this in disguise because you prove using Fourier analysis, but you can also show that what that proof is actually doing is solving the dual Delsarte LP, which is actually what they did here. They provide an explicit feasible solution for the dual LP that is quite good, and that gives you an upper bound.
Can you remind us what are the bounds?
Sure, I can. I was trying to avoid it writing, but since you want to, so the lower bound, GD bound, says that the rate of code is at least entropy. Oh, sorry, 1 minus the entropy of delta, and the lower bound says is the most entropy of 1/2 minus square root delta minus delta. So here I'm using rate. So by rate, what I mean is that this is log base 2 of size of the code divided by n, and you maximize over code. C such that delta C is delta N. So these are the bounds. They're not very nice. So if you're thinking of delta equals to 1/2 minus epsilon, which is perhaps the one that people study the most, then the top bound, these two bounds, they look like this. The bottom bound looks something like epsilon squared, and the upper bound looks like epsilon squared log 1 over epsilon. Okay, so there's a small gap here. Well, depends on people. People might think that this is small. You'll have to remember that you're taking a log, so it's small, but it's not too small. It's a change of basis, right? Okay. Right. Any other questions? Okay. So let's see what are these association schemes. So as I said, the objective of this talk is to actually see several different perspectives of this. We're going to see this is an association scheme. We're going to see this is a translation scheme, then a Schurian scheme. But I need to introduce to you all these constants. Here's the definition of an association scheme. So the first kind of idea of this is sort of completely combinatorial. So you're going to have some base set and a set of relations. So this base set is just going to be non-empty finite set. And the set of relations is going to partition X cross X into non-empty subsets. But not any partition. We're going to say, well, I want to see the diagonal relation. So the diagonal relation is one of the parts of the partition. It needs to have, every time I see a relation, the transpose relation should be in there as well. But what's going to make the whole thing actually not just, just a set with a partition of the relations is these intersection numbers. And what are these intersection numbers is like this. So I give you 3 relations, and there should be a number that's going to count every time I give you an X and Y on relation T. This is going to count the number of Z's such that XZ is in relation R and ZY is in relation S. And it should not depend on XY as long as I pick it in T. So it's some sort of regularity condition.
I'm sorry.
Yes.
A relation is a subset.
A relation is a subset of X cross X, right? So you can think of this, I have some vertex set X, and each of the relations a directed graph, right? So you can think of it as, I have a color directed graph, right? Each relation gives me a color, right?
What's the intersection number?
So the intersection number is some sort of condition of regularity. So for example, if you're thinking in terms of colors, you're going to say, right, okay, there's an intersection number that corresponds to red, blue, yellow. And what is the red, blue, yellow is going to be every time you give me a pair that has a red edge, then the number of yellow edges and then blue edges forming a triangle. So maybe let me draw. So you have, say, a red edge here, and then you're going to count how many points do you have that have blue edge here and yellow edge on the other side. So you count how many points you have this, and this should be exactly your P.
And it should be constant for every edge.
It should only depend on the colors, not on the choice of the vertices. So if I pick any X and Y that have red edge between them, and you count how many points have blue edge and then yellow edge there, you should always get this number. It doesn't matter which X, Y you chose, as long as you chose one that is with the red edge, okay? That's what the intersection number is giving. Now, there's some relation of this to, if you ever heard of coherent configuration association scheme is a stronger thing than that, and this is very much related with graph isomorphism. You can kind of tell because you essentially look at degrees of vertices, that gives you sort of one of the relations, and then you kind of try to reason about, okay, how many things between these 2 degrees have common degree something, and then you kind of start coloring your graph. But we're not going to be focusing too much on the combinatorial aspect because there's also an algebraic aspect to this. But is everyone? Oh yeah, go ahead.
Okay, I probably answered your next question. It's a bit too fast for me, and the writing is small, and I fear that I won't be able to follow the next 2 hours if I don't get this right.
Okay.
So, any chance we can go slower on the properties after the diagonal?
Yes. Yes. So okay. So diagonal relation.
All the diagonals, it's less that this is a partition of the.
Yes.
Yeah, I mean it's written, but yeah, it's not visual. So it's linear coloring of 4 possible edges on X.
Yes. So think as a coloring of the complete directed graph, right?
Bidirected.
Yeah, bidirected.
Right.
Yes.
And
Yes.
loops all have the same color.
What?
All the loops have the same.
Yeah. So the property 3 is saying all the loops need to have the same color, right? That's property 3. Property 4 is saying, well, every time something is colored in one way, if you transpose this exactly another color, right? So if you look at the red edge, there's another color called red transpose, and every time you look at the other direction, if it was red, it's now red transpose, right? That's what 4 is saying.
It's the same.
Well, okay, we'll get there. I will, if you want to think of a non-directed graph, you're free to do that. I will do that in just 5 seconds. It will be easier, but I will say something about it. So that was property 4 saying, and property 5 is saying this drawing here. So every time there is a number that only depends on the colors, and every time I give you some xy that has color red, and I count the number of vertices that have color blue here and color yellow here, I always get this number. It doesn't depend on the choice of xy, as long as they are a red edge.
This number is a property of triplets, right?
It's a property of triples of colors, right? Of triples of colors, but not of vertices, right? So it doesn't matter which vertices you pick, as long as they have a fixed color, it completely determines the count.
It'd be obvious that this is easy to get, possible to.
Well, I'll give examples. I will give examples in a second, but a spoiler is, Hamming cube will be one of them.
But even before, you must have seen like this, the basic thing is ratio. You suppose there are only two colors, an edge and a non-edge. And what you want is a number of common neighbors.
Yes, you can refine a graph towards this, right? How do you get, well, you don't get exactly association scheme, but let's just forget about that. Start with the graph, and then you say, okay, let's decide the colors of the diagonal, right? First, well, how do you decide this? You take the degree. So let's assume for a second that.
I was going to say, I'm already explaining the use of this. I was going to say something simple, which is capturing the definition. You have the graph, right? There are some edges, some non-edges, so these are two colors. And this property of having intersection numbers in this case, very special case, is that every pair of vertices which have an edge between them
have the same number of common
neighbors.
Common neighbors.
Common neighbors. And every pair which does not have an edge between them have the same number of common neighbors. And also neighbor to one and neighbor to non-neighbor to other. I did the symmetric case, so it's.
No, I'm saying you also need to get these right.
Yeah.
But yeah, so you can see it as some sort of version of strong regularity, this kind of thing, but even stronger. Okay, so is everyone fine with these 5 items? Okay, so then furthermore, we're going to say that this association scheme is commutative if these intersection numbers, they commute in RNS. Oh, sorry, this should be it. So it doesn't matter whether you PRST, I can do PSRT, I get the same number. Okay, so that's just a definition for a second. We will see why is it called commutative. And the other is symmetric. Symmetric, I'm going to say, actually, it's a graph. So the relation transposed is equal to relation. And for most of this talk, I'm going to actually focus on the symmetric case, but everything that I will say actually holds on commutative, except that you're going to have to do some adjustments.
Sorry. Commutative,
Commutative just means.
It means that if I take their blue, yellow, or yellow, blue, it's the same?
Yeah.
Yes, if you swap these two and you count instead yellow and then blue, you get the same number.
And just to, it feels like it should mean something if I'm looking at the Kelly graph of a group. So if I'm looking at the Kelly graph of a group, then does this means exactly like?
We will see why is it called commutative. There's a reason why it's called commutative. Not necessarily if you're coming from some symmetric thing. It doesn't necessarily give you commutative. We'll see this, but yes, you're on the right track. You're on the right track. But in a second, I'll tell you why it's called commutative. What is commuting? There are things that are commuting. It's just not clear from the definition. Okay. Is everyone fine with the definition of commutative and symmetric? So here's the mysterious fact. Symmetric actually implies commutative, which is not obvious at all from this definition, but it is a fact. And I don't know, maybe I'll prove it or not.
It's kind of like.
What?
Yeah, it can, from the drawing, it kind of looks obvious. Because it just reverse all the edges.
Right, okay, there is a combinatorial proof. Yeah, there is a combinatorial proof, but there's also an algebraic proof, which is also cool. But okay, yes.
Isn't just this.
No. So what is obvious is that I think this is obvious. If you do T transpose, then you do S transpose. R transpose, and then if it's symmetric, then you can. The transposes are the same thing, and then yes, okay. So then I guess this is the combinatorial proof. Yes. Okay. Nice. Okay, good. Right. So this is sort of the combinatorial view of an association scheme, but we'll also be interested in sort of an algebraic view of an association scheme. So every time you have an association scheme, you get what is called the Bose-Mesner algebra of it. So this is the matrix algebra. So R X cross X matrix algebra. Perhaps I should give it a name, AS, generated by these matrices AR, where AR is ARXY, is the indicator that XY is in R. Okay, so this is the Bose-Mesner algebra of an association scheme. You just take these matrices X cross X, and each of the relations gives you a 0, 1 valued matrix that indicator of the XY is in the relation.
Like it's one for each color.
Yes, one for each color, exactly.
And when you say the algebra generated by them, then like matrix multiplication and
Yes. Matrix multiplication and addition and linear combination, R linear combination. Okay, so I will say, so from now on, I will be assuming symmetric, but everything that I will do today actually holds for commutative, but you have to be careful because you have to define these over complex numbers and you have to take conjugates and in smart places. I'm not going to be doing this today, but everything that I will say actually holds over just commutative ones. But from now on, everything is going to be symmetric. I will give an example of something that's symmetric, but that's commutative but not symmetric in just a second. Is everyone clear with what is the definition of this algebra? Okay, so the point of all this is that you can see that there's a very nice property based off of the intersection numbers. If you just do matrix multiplication, you can check that these guys actually can be written very nicely like this.
Sorry, stupid question. Bose, is it the physicist?
I have no idea. I would guess not, but I have no idea.
Is it related to some kind of?
No, what you ask whether these guys are physicists?
The Bose.
No, the Bose is a combinatorialist. It's a guy from the BCH codes.
Okay.
Not
like a Bose.
no, it's not the Bose. It's not Bose.
Oh, no, yeah, this one I don't think it's, it's not the same.
No, it's
A lot of these things associated to.
Okay, so the nice thing about these intersection numbers is that, when you take the product of these two guys, is actually a linear combination of the original matrices. So this is nice because these matrices that you're using are not only a basis of the algebra, but they're a basis as a vector space basis. This is what this is saying, right? This is the first point of this. Not only that, now you can see what does actually commutative means, right? Because if PRST is equal to PSRT, it means that if you swap these two guys, you get the same combination. So the algebra is actually commutative. That's what it means, right? And that is the main property that we're going to be using. So when you have commutative, you get a commutative algebra, right? AS is commutative. And this means that if you have now a bunch of matrices that are commutative, you can diagonalize them simultaneously, right? So AS is simultaneously diagonalized. What we're going to do is we're going to say there exists, unique up to permutation basis ER prime of so basis of idempotent orthogonal matrices. Okay, so what do I mean by idempotent orthogonal matrices? What I mean is that if you do ER prime times ES prime, then what you get is 0 if they're different, and if they're equal, then you get just ER prime. Right? Because what you do is you simultaneously diagonalize them. So now in some bases, it's just a bunch of it's a diagonalized matrix, and then you can just say, well, what are the eigenspaces of them? So each of these ERs, at least after you change bases, looks like something like there's a bunch of zeros, and there's a particular block where there's an identity, and there's a bunch of zeros, and each of the E's are giving you a different block, right? So they're disjoint blocks. Yeah, they're disjoint blocks. So when you take their product, if they're different, it goes away. If they're not different, then you just get the same, right?
Idempotent orthogonal means orthogonal projection?
No, orthogonal means you take their product. If they're different, it's 0. In the symmetric case,
these are orthogonal projections.
Yes, in the symmetric case, the thing that the simultaneously diagonalizes is going to be orthogonal. In the commutative case, in general, it's not, but in the symmetric, yes. And idempotent just means, take the product of it with itself is just itself. Right? Idempotent is the usual way.
That's what we call orthogonal projections.
Right.
Okay.
I'm refraining to say orthogonal because if you use the natural inner product, then maybe it's not actually orthogonal in that. Right? But whatever. Okay. So now this gives us a different basis, right, for this algebra. So this means that I'll write it here, I guess. This means that we can define some functions that do the change of basis for us. So these are what are called the P functions and P functions and Q functions. And what are these? Well, okay, so the P functions, they're going to be indexed by relations, and they're going to go from this sort of, you want to think of this as a set of dual relations. It will really become set of dual relations in a second, but these P functions go from these dual relations to real numbers, and the Q functions are the dual version of that. So they're indexed by dual relations, and they go from primal relations to real numbers, and they do the change of basis. So the P functions are responsible to saying, if you want to write AR as a linear combination of the E S primes, then you should use these P functions. And if you want to write the E R primes as a linear combination of the ARs, then you should use the Q functions, except for some normalization. The ERs, you want to do some normalization. Okay, so these things exist because you have these two vector space bases, right? Okay, I didn't say that this is a vector space basis, but it's sort of clear because they're idempotent. So you have two vector space bases of the same space. So there is a unique choice of P and Q functions that does this change of basis. Right? And the final.
We've never seen it. But it looks very similar to the Fourier transform.
Yes, I was going to say that it is similar to a Fourier transform, and we will see some orthogonality properties of them in a second. Okay, so it's just that it really is similar to the Fourier transform in the sense that there's a Fourier transform and there's an inverse of the Fourier transform, which is not necessarily equal to the Fourier transform itself. But related. Yeah, but related.
It's really, I mean, just for analysis, you think that the matrices are cyclic matrices, which commute with each other, cyclic, just all rows are just shift nodes.
Mm-hmm.
prove the first law, then Fourier transform will take them to a parallel matrix, and the inverse will
Right.
come back and look very simple.
So just before, so I'm purposefully not revealing the last board here because there's things written there. But let me just do a final definition, which is to say, imagine that I give you another scheme S prime. It's over the same set X, but the relations somehow are indexed by the dual relations. We say that this is a dual of S. If P functions S are Q functions of S prime and vice versa. Well, you know, the vice versa is actually in parentheses because if you get one, then you get the other. You don't need to prove both, but okay. So just this definition, it's not necessarily true that every scheme has a dual, and we will see examples. So let's see some examples of schemes finally. So okay, so
I think I'm missing something because up to this point, our primes were just an index set.
yes, so I'm cheating a little bit.
It had nothing to do with
Yes.
subsets of X.
Yes, I'm cheating a little bit. What I'm saying is that, you know, there's a choice of relations and there's a bijection that you say, this relation corresponds to this index set on that one that does this. I'm cheating a little bit, but yeah. There's a bijection that makes them be duals. And when you say dual, you actually need to present the bijection. You need to say, this dual, this relation on the dual scheme corresponds to that index there, and etc.
I'm just want to make sure that I get it correctly. So far, the S prime in R prime doesn't represent a certain relation. It just
yes, there's no reason why there is a dual.
Just some index.
Yeah, there's no reason why there exists.
We have a way of saying, okay, this is actually we can match this thing to some other.
You don't always can. Sometimes you can't. Some schemes do not have duals. But when they do, you say dual. It's the dual. Okay.
Most schemes have a diagonalization of the algebra.
Yes, but the issue is essentially
commutativity automatically gives me.
yes, but the issue is that essentially you get sort of all the dual notions, but the problem is that the intersection numbers they need to be integers, right? And sometimes when you do the dual thing, you get that the corresponding intersection numbers of what would be the dual are not integers. And you're like, okay, so there's no dual because, right, the association scheme, it should be a count of something and it's integer, right? So sometimes you don't have duals. We'll get there. It's the third example of a case that there is no dual. So let's see some examples. So the example that we'll mostly be concerned about are the Hamming schemes. So I'll tell you two Hamming schemes. We'll mostly be focused on the binary case, in which case both of the examples are the same example. But let's start with the weak Hamming scheme. So the weak Hamming scheme, what we're going to do is, well, we take some finite field f, and we're going to look at f to the n, right? So words over f of length n. And what is going to determine a relation for us is going to be the Hamming distance, right? So what we do is we say, well, the relation set is the set of Ri's, and each of the Ri's is the pairs such that the Hamming distance is exactly I, okay? And then this gives you some scheme, okay? This is the weak Hamming scheme. You just measure the distance, the Hamming distance. If it's one, it's one relation. If it's two, it's another relation, etc. Right? So it's easy to see that's a symmetric scheme because, you know, Hamming distance is completely symmetric. It's not so easy to see, but this is actually a self-dual scheme. And because it's self-dual, the p's are equal to the q's, and it turns out that they're actually what are called the Cauchy polynomials, which is this formula here, some alternating sum of products of binomials. It's not that important what these things are. It's just so that you have an idea of how complicated they can be.
Just the fact that I have this triangle condition.
Yes, you have to check it. I'm not going to.
It's just because I'm not working on some homogeneous space. So it's.
No, you're working over the Hamming cube, but over not Hamming cube, but over a finite field, right?
That's homogeneous. That's something that doesn't care if you,
Yeah.
no matter how you look at it.
Yes.
At any point looks like a neighborhood of the,
Yes.
a neighborhood of the origin. So
Yes. So you're kind of spoiling the definition of both translation schemes and assurance schemes, which will be very much in the later part of the talk. But you're absolutely right. That's one way of seeing that the intersection numbers make sense. Yes. Okay. Now you could do something more complicated than the weak Hemming scheme, which is the strong Hemming scheme. There should be parentheses here. Which is instead of just measuring the Hemming distance, you actually measure how many, what is the difference of these two words. So you take the difference of the two words and you say, well, if I look at the difference, how many zeros do I see? How many ones do I see? How many twos do I see? And that's what determines a relation, right? So there's a relation saying, oh, this relation is every time you take two words such that when you subtract, you see 5 positions have 0, 7 positions have 1, I don't know, right? Something like that, right? So this is the strong Hemming scheme. This is not symmetric. It's well, unless you're over a field of characteristic 2, but whatever, in general, it's not symmetric.
it's that you have some kind of convolution, right? Just taking the minus, the vector to minus in this field.
Yes, but that does not give you, that gives you another relation, which is one of the properties that we're saying, right? So if you flip the transpose relation, it's still a relation, but it's not the same relation, right? So that is, you're checking the transpose relation, but it's not symmetric because it's not necessarily the same, but it is commutative at least. It is also self-dual. It's not easy to see. And the P and Q functions get even more complicated. It's this nonsense. So just to have some idea that it can be really bad. And as I said, right, when you have commutative and not symmetric, there's some character here. So you actually have something that's complex valued. But don't worry too much about it. This is just to say, the P and Q function can be really complicated. Now, the thing that I want to note about these two examples is that there is sort of a gain in encoding, because if you look at the spaces, both of these are over f to the n, right? So it's an exponential sized space. But if you're going to compute these formulas, they can be computed in polynomial time, because these sums are just polynomial sized, and whatever you're doing inside is also polynomial. So this is sort of the gain that you expect to get, is that somehow everything is being coded by something that's much, much smaller, much easier to compute, okay? Even though we're not gonna be focusing too much on the algorithmic aspect, this is one of the advantages of using this.
Can you please elaborate on that? What does it mean everything can be encoded?
Yeah, I will get to the Delsarte LP. The point is that, if you just wanted to try to upper bound a code, you would use some very basic graph theoretic, like optimization techniques. And if you did that, you're working over an exponential size space. But there will be an analogous optimization thing that will be over only polynomial size things in N, right? If you're working over the Hemming scheme, if you just do it flat, you're going to get something that's exponential in size, and then it's really bad to actually run. But there will be another thing that comes from this association scheme theory that is just going to involve these P and Qs, and they are very easy to compute in the Hemming scheme case, which is just polynomial time computable, and the program will be polynomial sized as well.
If you think just of a binary code, you can describe the whole code. And you can describe something much smaller, is how many pairs are of distance,
yes.
Or how many pairs are of distance, 1 just n plus 1 number.
Oh, so you're saying like I don't need a description of, say, generator metrics. Here I have circuits to compute P and Q.
The generator metrics may give other information, and it's not restricted to linear codes. I mean, this encoding, it's just a part of the information about the code is just these numbers, which are just n plus 1 instead of potentially 2 to the n, describing the whole code. It does not describe the whole code or scheme. It's just information that's useful for some purposes. And in general, distance numbers, these are the P numbers.
Yes.
The P numbers are functions, right? We have efficient algorithms to compute the function.
Yes, but there's only polynomially many relations, and so it's a table, polynomial sized. and each entry is computable in polynomial time. So you can compute these things very fast. Of course, they don't completely encode the thing, but they encode the space up to some loss. And we'll see that there's a similar way of encoding a code up to some loss that you can still get some optimization problem that will give you an upper bound, but is much, much faster than just doing it flat on the full space, because the full space is huge, it's exponential size.
Okay, so you're saying, when you're saying they encode the space up to some loss, you're saying they encode the association scheme, the algebra.
Yes, yes, that's it.
They call the part of it. It's not
Yes.
yeah, it has nothing to do with the coding, with the codes that we are
Yeah.
talking about.
They have some information, let's put it
Just
very
some
vaguely.
useful information about that. Yeah.
Okay. Right. So the third example, which will not be focusing at all, but just for completeness to have one slightly more weird, but still very natural example, is the Johnson scheme. So in the Johnson scheme, what you do is you take all subsets of a certain size of brackets n, and the relations are essentially the same as before. You just say, well, two guys are in a certain relation if their symmetric difference is equal to I. So another way you can interpret is you take binary strings and you say, well, all the things that have a certain Hamming weight, and the relations are just computing the Hamming weight of the difference. This is very easy to see that it's symmetric, just because, you know, symmetric difference is a symmetric thing, but it has no dual. Now, proving that it has no dual is you do the computations and you see that what was supposed to be the intersection numbers of the dual guy is not even an integer, so it certainly has no dual.
Is it very complicated, or can you explain how do you see the self-duality in this case, in the simplest case, in the Hamming disk?
Oh, no. So the self-duality comes from the p's are equals to q's, right? How do I compute this formula? We'll get to an easier way of computing this formula. At this point, if you wanted to compute here, you have to do.
If the p is equal to q, it is its own dual.
Right, because the definition of dual says the p functions need to be the q functions of the other. But if I compute this, I don't know how I computed this, but I claim that, you know, if you do PRI RJ is the same as doing QRI RJ. So it's self-dual, right? Because it's the p's of it are the q's of it, so it's self-dual.
I'm not sure what is the IJ. It's like, I'm sorry, because the way that you define the PK and the P's and the Q's, you start with an auxiliary index set, which is called R prime.
Yes.
Now you tell me this R prime is R.
Yes.
And
this is the bijection, because as I said,
what is the bijection here?
The bijection is there's some index and I can index it by the relations themselves.
You see that these relations are defined by indices I or J, which are just the sizes of the Hamming disk.
Yes.
They are not abstract as they were.
They are the sizes.
Yeah, that's how we define it. It's a concrete scheme.
Yeah, Ri is the pairs that have distance exactly I. This is the relation R, right? Okay, but then there's this abstract thing that I construct this R prime, but I'm going to say, well, let me index it based off of these Ri's that are the the primal ones, right? And I say that if you index it like this, you're gonna get PRIRJ is going to be QRIRJ, and it's going to be that form.
So essentially you're telling me I have a way of indexing them.
Yes.
Such that the Q's would be equal to the P's.
Yes.
And then I won. And then
yes.
This gives me the bijection.
Yes.
Okay.
But notice that
you're not telling me here what is exactly those projections and those,
here I'm not telling you exactly this.
Okay.
But a priori, you're absolutely right. I should be, if I wanted to be more formal, I need to say, yes, okay, here are the explicit projection matrices, and I'm going to say, okay, this one corresponds to the zero relation, this one corresponds to the one relation, etc. And if you do this correspondence, then the P's match the Q's.
Yeah.
And that would be the.
We don't care about it.
Are they easy to write? In the simple case, it's like small number n or
what the matrices?
Those projections, yeah.
We will see. Okay, I can spoil it. This case is actually very easy because the Hamming scheme has an abelian group structure. So one way that you can easily see that this is simultaneously diagonalizable is by just doing, representation theory. So the E things will be related to the characters. So that's how you could see this, but this I was going to say way further in the presentation. But yes. But this, don't worry too much about the specifics of this. Even these formulas at this point they're very mysterious, but they will come from a much easier way of computing this.
I think we actually saw this formula in the teaching seminar, you know, when I don't remember which talk, but they had this formula for, you know, the Walsh representation, and it was used for something. I don't remember.
Talked in the fall, he described, I mean, that's essential for the Delsarte, which Leo will remind you all about.
Yes.
Wait, so in whose talk was this?
Fernando's.
Okay.
So in this talk,
So not very surprising.
yeah. So in this talk, I'm laying down the basics of the theory, but the point is to present the joint work with Fernando. So it's not surprising at all. Okay. Any more questions? Okay. Let's see. Okay. So now what I want to say is, I guess I go to the next. All right, okay. So, as Avi suggested before, there's a very natural analogy of these P and Q functions to Fourier transforms. And the analogy is even stronger than you might see at this point. So at this point, you're just saying, okay, is a change of basis. But actually, there is some orthogonality relations that are happening behind the curtains here. And for those, I need a couple of random facts and some definitions. So first, here's a random fact, which I will not prove, but so there exists a dual diagonal such that if you compute the D matrix, the E of this dual diagonal, you get exactly the J matrix over X. Okay.
What is the J matrix?
J is the all ones matrix. Okay. So there is this, and this is actually when there is a dual scheme, this is actually the dual, the one that needs to be mapped to the diagonal.
The square root of X?
No, it's X. It's X. It sounds mysterious, but it is X.
It should remind you of the Fourier transform, where the Fourier transform of the delta function at 0 is the uniform vector.
Another way,
It's a projection on the all one vectors.
yeah, but it needs to be idempotent. If you take this times itself, it's equal to itself. Okay. Okay, so this is a random fact, and we're going to define a couple of things. So first is the valency. So valency of R. So this is VR. So again, R, some relation. This is just going to be the size of R divided by X. Another way of seeing the valency of R, if you think about it for some time, you're going to see that this is the same as this. And this is a definition. This is an observation. This is a less trivial observation. Oh, sorry, it's ER. This one I'm not going to prove, and you need to know exactly how this works to prove that. And the other, so is the dual version of this multiplicity. MS. So I'll try to put primes every time it's a dual, but I might forget at some point. So this is just a rank, S prime. Because these are idempotent matrices, the rank is the same as the trace. And as you might expect from this formula, this is this as well, which I'll not prove, but it is. Okay.
Right.
No, these are just definitions, right? So valency is saying, what's the size of the relation morally?
Yeah, but then you're equal to.
Yeah, this intersection number, this you can show because, you take X and Y, right? And they need to be diagonal, so it needs to be X equals to Y. And then you need to count how many z's relates to that. Well, it's exactly the size of the relation, but you have to divide by x, right? Because you're fixing one of the points.
And then the last one is just how you.
The last one is.
That's how you write it down.
No. Yeah, this is compute the p function at this dual diagonal.
That's the, okay, that's the p
I'm not
function.
going to prove this, but it's a fact. Okay, this one I'm not proving, but.
No, I understand the notation
And the multiplicity is the dual version of this, which is instead of computing the size of the dual relation, because it doesn't even make sense a priori, you compute the rank of this matrix, which because this matrix is idempotent, it's just a trace, and the dual thing also holds, but I'm not proving this, okay? So the point here is that what we want to show is this weird orthogonality relation. So first, you have orthogonality of the p functions, but it's not, they're not flat. Orthogonal, you actually have to put multiplicity here. So now it's orthogonal, and it's not orthonormal either. That's some norm. It's not one. That's the first, and the second is the dual of this. So I might expect so this one I'm actually going to prove. It's just a manipulation, and I'm actually going to prove. And I think here, just as a cheat sheet, there's nothing. Everything that I said is over there, just so that I can start erasing, and you don't have to remember it.
Yeah, the Zoom audience will not see this.
Oh yeah, so Zoom audience, there's a link.
You can see it. I'm here.
Oh, okay. Yeah, there's a link, but I already raised the link. But you go to my page. Go to PDFs, and then you go to AS side, and you will see everything that's on the sideboards. Okay. So let's see that. Okay, so let's give a proof of this, and it's just manipulating these expressions. So one, so we have the sum, the balances. So that's wait, it's the multiplicities first. Okay, so we're going to do this, so there's not much to do. I'm just going to open up the definition of the multiplicity, and particularly I want to use the trace one. So I'm going to do this. I'm going to put it all the way on the right. So we have trace of EP prime. Okay, so, but the point is that the ETs are idempotent orthogonal matrices, right? So I can do this cheeky little trick where I say, well, let's take a T1 and a T2, and let's use T1 for P, R, and use T2 for yes, and do trace of ET1, ET2, right? Because now this guy only survives if the T's are equal, right? So that's just a trick. Now I just trace is linear, so I can put everything inside. And what I'm going to get is Okay. But now I can use the definition of the P functions and say, haha, this is just the AR matrix in disguise, and that's just the AS matrix in disguise. Right? That's the definition of the P functions. But then we also know how this product takes place, and it's linear. So this just gives you sum over T in R, PRST of trace of AT, right? But now again, the ATs, what are the trace of the ATs? The only matrix that actually has a trace is the diagonal matrix, right? And in that case, the trace is exactly X, right? So you get X, and you need to see the diagonal. So you get PRS dx, and that's it. Yeah, you get this. Yeah, you just get this, right? But what is PRS dx? Well, it's you take X equals to Y because it's over the diagonal, and you count the number of Z's such that they relate as R to X and they relate as S to Y. Well, but X is equal to Y. So this means that this can only be X PR R transpose dx 1 of R equals to S. I'm assuming symmetric, so maybe it's equals to S transpose, but I'm assuming symmetric. And then this is the valence. This guy's the valence. Okay. So just by manipulating all these definitions, we can get this weird orthogonality of the P functions. Okay.
It's also weird. It's a weighted orthogonality. I mean, it's
Yes.
orthogonality according to
Yeah. I mean, weird in the sense that maybe you were not expecting it, but you should be expecting it. Not in the sense that, you know, this is normal. The fact that you have to weight it is completely normal. Okay. So how do you go by 2?
You want to do 2, yeah.
Actually, I prefer 2 than 1. 1 is sort of the preparation for 2. The one that I care about is 2, not 1. So let's do 2. And for 2, I'm going to Q R E prime T. Okay, so what I'm going to do is I'm going to do the last step of this thing backwards, right? So I have some sort of expression for VR going on here, and I'm going to use this here. So what I can do here is I can say, well, this is the same as saying sum over T1, T2, and R, Q R prime, T1, Q S prime, 2, trace of AT1, AT2, except that I have to normalize by the X here. So I think I'm missing over X. Okay, so this is sort of the last step backwards, right? If you notice the last step backwards, you do X VR, you trace it back and you're going to get to here, I guess here. So this is the last step of the previous one backwards. Okay. So now I'm going to do the same kind of thing and pull the trace out. So this.
Previous line you got T1 and T2 as product.
Now everyone, T and T1 or T1 equal to T?
No, so this thing, the point is that this thing only survives if T1 is equal to T.
Okay.
Right, and when it survives exactly with the valency divided valency times X, so it cancels. Yes. So it's the last step of that backwards. Okay, so you get this times T1. A little bit more space. Because I want to put 1 over X here, and I want to put another 1 over X here. And then I have this X to compensate. Okay, So this is just opening up by linearity. And now again, what happens is that this just are the E matrices in disguise, right? So that's the sort of importance that you get these normalization right. So you just get trace of E R prime times E S prime. So now this is easy because these are all equal to matrices. So, and you're just gonna get one that they're equal, trace of one of them, which is exactly the multiplicity. Right. So that's the other one. That's the other orthogonality. Now you could also cheat and say, well, if you only care about the Hamming scheme, then it's self-dual, so one is immediately true, but in general, you don't have to do that. Okay. Any questions about this? Right. Okay. So the reason why we care about this is because this is what is going to lead to what are called the MacWilliams inequalities. So remember that we're actually interested in codes. So we're going to use the inner distribution of codes. Just gonna say that the code in S is a non-empty C container X. Okay, so this seems sort of silly because it's just a subset of X. Why are the relations even relevant for me? Right? I have some weird structure over X. And the code has nothing to do with it. Well, the point is that we care about what is called the inner distribution of S.
What is S?
S is the scheme. S is the scheme.
S is that something?
S is the scheme. Okay. Yeah. Throughout this, S is always whatever scheme I'm working on. And the point is that we care about the inner distribution of this code, which is a function, AC, from relations to like real numbers. And it's defined by saying ACR is you're going to count how many pairs of code words are in R, and you're going to do this normalization by C. Okay. So that's this is how we're going to use the scheme, the structure of the scheme to actually study this code. I'm going to say, well, okay, I just count how many times I see edges of each of the colors inside the code, between code words of the code. Okay.
So in the simplest case of the Hamming distance, this would be just how many words I have of distance.
How many pairs?
Yes, how many pairs of words you have of distance 1, how many pairs you have of distance 0, there's distance 2, etc. You're keeping track just of this information. Forget everything else about the code and you keep track only of this, right? So the point is that you get what are called McEliece inequalities. Well, let me just. What? Oh, I'm not talking about linear codes. Yes.
No, I know, but it's inequality. So it's
for general codes, it's inequalities.
okay.
Because I'm not talking about linear yet, but you're absolutely right. Okay, so just some small observation. What is ACDX? Well, it's code cross code intersection diagonal, which means it's just XX for some X in the code whose size is just C, right? And then you divide by C, so this is just 1, right? So this is just a trivial observation, but it will be important. So what we're going to do now are what are called the McEliece inequalities. We say that, well, if you do what is called the Q transform of the code, so you take some dual relation and you take the Q functions and you do the Q transform of this inner distribution of the code. If you do this, you always get something non-negative. That's what the McEliece inequalities are going to say. So, okay, sounds very mysterious, but let's prove this. So, okay, so
the inequality you have the, is it S prime or what? It's like, you have
Yeah, there's a
free parameter for any S prime.
Yes. So that's why it's inequalities, not inequality. It's more than one. Okay. Okay, so there's not much to do here. What we're going to do is just open up the definition of this. Yeah, sure. Here. So what I want to do is I want to say I want X to be in the code, I want Y to be in the code, and I want them to form the relation R, right? So this I can just write it as ARXY. Okay. Now, so here's a advice from my previous advisor. Every time you see two sums, you just swap them. You don't think about it, you swap them, and then you see if something went wrong. And typically everything will go correctly. Let's just swap these sums. See here. So you have 1CX, CY, and here's here. Right. And then you see that it was a good idea to swap, because now again I get the E matrix in disguise, except that perhaps I'm missing an X. So well, okay, I get an E matrix in disguise. Yeah, I guess yes. You just get the E matrix in disguise. Right.
When you write the matrix XY, that's the entry, that's the XY entry of
Yes, the XY entry of the matrix. Right. So this is just a Q combination of the A matrices, which supposedly is just the E matrix, except that I'm missing the 1 over X, so I just adjusted that. Okay, but now I'm done, because this is nothing more than 1C transpose ES. C, which is greater or equal to 0, because these are idempotent matrices, so they are PSD, right? So that's the MacWilliams inequalities. What you're doing is you're doing sort of a change of bases. This is just computing the quadratic form in the E basis. That's what this is doing. Okay. So that is nice. Okay, so why do we care about these MacWilliams inequalities? Well, it's because now we can use this along with optimization to provide upper bounds. Right. This is finally what is called the Delsarte linear program. So remember, our objective is to provide some upper bound to codes, given that we know something about the distance of the code. So just a small definition, imagine that I have some D that is contained in R, and let's also say that it contains the diagonal, otherwise it will be a little bit degenerate. What I'm going to say is that the D code,
this is a subset of the relations.
yeah, subset of the relations. A D code is some code C such that the support of AC is contained in R. Right? And the idea here is that, in the Hamming scheme case, oh, sorry, in the Hamming scheme case, I'm interested in codes of distance at least delta, right? So what do? I say, well, let's take d delta to be 0, delta plus 1, etc. up to n, and this is codes of distance delta is the same thing as a d delta code. So that's this definition. I'm going towards this,
You don't allow pairwise distances less than that.
Yes, you do. These are the allowed distances. So it's saying either it's 0 because it's the same code word, or it's delta plus 1, anything larger than that, right? So this is what this is. If you look at the way Delsarte calls them, they call them M cliques for some M, which is D in the case, D cliques, because he's really thinking about the view of a graph, right? So you can think as it's a clique in these colors, but you know, going more towards a coding theory thing, you can call it a D code. And the point is that you get the Delsarte LP. Every time you have a D like this, you get a Delsarte linear program, which is like this. You maximize sum of ARs R such that take this guy to 0. You want ADX to be 1, AR to be 0. B, AR to be greater than 0. The point of doing this is
maybe you want to write this, the sum of ARs is the size of the code.
yes, I was going to say exactly this, right? So the point is that if C is a B code, then AC is a feasible solution value. Well, how much is this? Well, sorry,
For if you will take only those in D in this case.
it doesn't matter.
It doesn't
Because,
matter.
so you get, you know, C cross C, enter R over C, you have the sum. But of course, the sum kind of gets rid of that, so you just get C cross C over C, which is. In other words, what you can say is that the size of the code is always less or equal than the optimal value. Right? So that is the point. The whole point is to use exactly this Delsarte LP to provide upper bounds for codes.
Can you repeat, what is this LSD?
It's this linear.
So
This linear
it's a relaxation of the problem of finding the largest code of this under this condition.
So consider this linear program. Okay, just this is the definition. Right? Maximize this.
I'm not trying. Maximize this.
Maximize the sum of ARs. So the variables are ARs, right? And subject to these conditions. Okay. Now the claim is that if I give you a D code, the inner distribution of the code, you can plug it in and it's a feasible solution. Why? Well, this is MacWilliams inequalities that we just saw. This we also saw. It was the trivial observation here, right? AR is equal to 0 for every R in R minus D is exactly saying that it's a D code, right? The support is contained in D, and greater or equal than 0 is obvious because it's counting something, right? ARCs are counting something, right? So these guys are always feasible solutions. What is the value of the feasible solution? The ARs are not necessarily integers because there's a normalization.
Yeah.
But also
But you
put
can
the
think that
condition in the linear program with
What?
you cannot put the condition.
Yes, also. But it's okay to think that they should be they have some integrality in them,
Yeah.
but you cannot really program that. So right, it's a relaxation because you say, okay, integer programming is hard, right? But the point is also that the value is size of code, right? In other words, if you just take the LP as this, compute the optimal value, it's always an upper bound for the size of a D code, right? So if you want to.
So what is an optimal? The optimal is the
maximum of this value
Yeah.
under this condition.
Plug it in your favorite solver, it's going to spit a number and you're going to know that the codes are at most something. And there's no reason why this optimal is actually integer. So you can even round it down because you know that the size of the code is going to be an integer, right? So I don't know, some Delsarte LPs give you like, I don't know, 7.2. And you're like, okay, it's in most 7. Okay, so this is the Delsarte LP. So any other questions? It might be actually now a good point to take a break.
Still talking, but I've got many questions.
Yes.
Leo is on the gas and I'm on the brakes.
What?
Yeah. Repeat the second line, you have QS prime, right?
Yeah, QS prime, yes. Oh, I should put it's for every S. Yes, here.
What's all the MacWilliams in it for?
Yes.
Yeah.
I guess one of them is true. If you take the dual diagonal, it's obviously true because, oh, I didn't write, but this guy is the constant one function, and this guy is also the constant one function. Prove that. So if you plug the constant one function here, you're gonna get this trivially true, but
From the non-negative.
yeah, from this.
And you want an association scheme where the Q functions are efficiently computable so that this is an efficiently network.
Well, a priori, right? Well, we'll see that in our hierarchy, they're efficiently computable at constant levels, but the completeness only happens at non-constant levels, in which case it's not efficient at all to compute. But yes, but a priori.
And this doesn't depend on the efficiency of the P functions, right? Only
It does. Sometimes you get P functions that are hard to compute.
yeah,
I said the program doesn't depend on the P function. No.
Well, you have to compute the Q functions, and the Q functions is morally just as hard to compute as the P functions.
Right, I take your word for it.
What?
I mean, okay, thanks. I take your word for it.
Yeah, no. So for example, in the Hemming scheme, it's the same, right?
Yeah.
There's a few. But you need to know how to compute these fast, and it's not necessarily true that it's easy to compute. There are other formulas, but I'll give you in the second part of the talk. I will give you a formula in a particular case, but you will see that the formula that I give you is not efficient to compute. But sometimes you can massage and get like formulas that look like this, right? And now this is efficient to compute.
I always prefer writing them as matrices everything other than summations. I mean, like Q and P are matrices, they are the basis changes.
Right.
This is a matrix times a vector. It looks like a linear program.
Right. Okay.
Okay.
But then you cannot write these formulas. Right?
No, eventually you have to write something, yeah. But what are the answers of this matrix? Yeah.
Yes. Okay.
But I mean the notations and also, in fact the proofs also, in matrix language sometimes just well, it takes less space.
Sure. Yeah, but I also am a proponent that when you do matrix computation, even though it takes less space, people look at like, wait, each equality costs n squared, right? Instead of O of 1, right?
So are you going to use an association scheme other than the obvious one in order to prove something for codes?
Yeah, well, so we're not actually going to use the Hemming scheme itself. We're going to use like a buffed version of the Hemming scheme.
For the hierarchy.
For the hierarchy,
This is just yeah.
So the point is that the code lives on the Hemming scheme, but you're going to construct a hierarchy of association schemes that are somehow tied to that. And then that's why it's important to know all these things. And we're going to see several different views of the same scheme. Well, not technically the same scheme, but several different views of what's going on the Delsarte LP. Cool. And it's important for the actual proof of completeness because the basic way of seeing it is not very useful to completeness. It's useful to actually run the program, but not to do completeness.
So do you have an example of a scheme that does have a dual and has nothing to do with the Hamming cube?
Well, you can cook them by hand, but then they're not very natural. I do not know one out of the top of my head. Yeah. There are a bunch of examples in the literature. If you look in Delsarte's paper, you can find it. But I mostly care about these three at this point. So
So I think sometimes it is useful to have this dual with fractional values.
Yeah, these are called, I think, called crime duals.
So,
you can-
you want integer, I want integer, but still something valid.
Yeah, so I skipped this, but there's something called crime parameters, which are the dual version of the intersection numbers, and you can do theory, like even though you don't have a dual, you can kind of pretend you do. Because everything, like there is.
There are not relations, there are,
Yeah.
functions to probabilistic relationship.
Yes, it's something like that.
So your email, didn't read it, but I'm very interested.
You start.
Yeah, well, 5 minutes past, I think, yes.
Okay, so, right, so remember we have all these weird formulas for the Hemming scheme, and at this point they might seem a little mysterious. You could trust me and say, okay, maybe he did the calculations and did the simultaneous diagonalization, found what are the coefficients of the linear combination, and then presented to us what is it. Actually, I didn't do that because I kind of used the cheat, which is the fact that the Hemming scheme is actually a much better behaved scheme than just a flat, symmetric scheme. It's part of a family of schemes called translation schemes. So what is a translation scheme? Well, it's a scheme, but X has a abelian group structure.
This is an abelian group, what you say has a structure. This is an abelian group, right?
Yes. I mean, you put a structure on top of X. It's not just a set. It has an abelian group structure, and we also want that for every R in R is X invariant in the following sense. X, Y is in R if and only if X plus Z, Y plus Z is in R. So for every X, Y.
R is just a subset of X, in a sense.
How is the relation?
It's a relation.
No, that's why I'm saying once you're specifying the relation R as.
Yeah, so that was going to be the.
In this case, it would be like the.
Equivalently, there exists some function fs from X to R such that xy always belongs to fs of X minus Y. So it's completely determined by their difference, which is what happens on the Hemming scheme, right? You just take the difference of the two code words and you measure something about their difference, but you don't care what the words were. You just care about what are their difference, right? So this is what the translation scheme is. So in fact, all the examples that we saw here, the two Hemming schemes and the Johnson scheme, they were all translation schemes. Right, because every time you did a subtract, okay, I get it. Yes, this one is not a translation. This one is not a translation scheme because the space does not have a group structure, a natural one, because you leave the space, but it's almost a translation scheme. Okay, now the point is that for translation schemes, they have very nice properties. So first, which is not trivial at all at this point, is that they always have the loop. They always have.
Don't you want to say before that the multiplication table of a billion group is, gives you this relation?
Well, but you don't. If you just do the multiplication table of a billion group, you're not necessarily going to get commutative, right? You have to bundle up some of them, right?
No. If the group is a billion, you will get commutative, and if it's a general group, you will not.
No, I don't think you get commutative. Because you're acting on the diagonal.
So just so we agree, the relations would be whether a pair multiplies, x times y inverse, or like you said.
Yeah, x minus y
It's
is equal
just
to
it's x minus fs is the identity. So these are.
Oh, sorry. You're saying commutative, not symmetric. Yes, commutative. You're gonna get.
Yeah.
Yes. That was you're absolutely right. That was my next observation. The translation schemes are always.
Yeah.
Translation schemes. Which is necessary for the P and Q functions to be defined. They're always commutative. You're absolutely right. This should have come first. They're always commutative schemes. Another way that you can see that is always commutative is because, as I said, it's very easy to provide the simultaneous diagonalization because now you have an abelian group, so you can just consider the character basis, right? The character basis is going to be a basis of eigenvectors of all the matrices. So you can just bundle up the eigenspaces according to what you see, and that will give you the matrix. Based off of this, you have these nice formulas for the P and Q functions. So knowing that is the character basis, you can get these formulas like this. So imagine that I give you some word such that fs of x is equal to r. Then what I can show is that Q, well, I'm not going to show, but there's a fact. This you can just do this. And if you have a word that gives you r prime, then you can compute the P function. Need to be completely pedantic, and I'm going to conjugate here, even though we're going to be working with symmetric.
Okay, I insist on this group relation.
Yes.
If you take the multiplication table of a group, any group, then what you have inside, you have elements of the group. So each relation picks up one of these elements. So these are matrices, right? For every group element, you get the matrix of zeros and ones, and you put ones in the place where, I don't know, G appears. So just a multiplication.
Yes.
The regular representation of this.
Yes.
And so in an abelian group, these elements,
it's representation of the
group. In an abelian group, this is diagonalized by the Fourier transform.
Yes.
So that's what is being said here. Now the characters are just.
Yeah, it's just slightly more complicated because the relations will not, equal to a certain G, but equal to G in a certain set. Right?
Yeah.
But you're absolutely right. The easiest case is when it's equal to a certain
It's
G.
a general case, right? Everything if it's a function of the group element, then.
Right. Yes, sure. Okay. So these are actually the way that you should compute the things that are behind here. It's much easier to compute this. But let's note that, if you're going to plug it in the computer, you're not going to compute it like this because this is still extremely inefficient, right? You still have to range over all possible code words or possible points of the space. So you don't actually want to compute this like this in your computer. You do it by hand and you get the formulas and you use the other formulas that are much more efficient. Right?
Yeah, just in the Boolean binary case, scheme. The P and Q are the Aldemar matrix, the one you like, the Aldemar-Wolf matrix.
Yes.
Both of them are. They're inverse of each other, except for the 1/2. Yeah.
Not in the Hamming scheme, just if you take the full group, right?
If you take the full book, you'll do, yeah, very good, thanks. Yeah.
Because you still have these binomials.
Now we get to.
But in the full group, you kind of get just this. Well, if it's binary, you also don't get this. So you just get -1 to the t, something like that.
You keep mentioning like the size of the LP and plugging it into a computer.
Yes, but we're not going to actually.
It's not something yet.
We're not going to do that for our hierarchy, but the point of this is that you could actually plug in the computer. People do that to get.
Will it give you any general relation between the rate and the distance?
Well, it will give you for a fixed n, right? You
Yes.
have to fix the n, and then you say, okay, on codes of block length 15, distance 6, have size at most whatever the program returned.
But for the type of bounds you want to get.
If you want to do an asymptotic bound, then this doesn't give you anything, right? But
No,
there,
it will be for a course in dimension n, block length n. You need to write a program that's polynomial in that, not exponential.
Yes, but
yeah, so from a practical standpoint, this is
Yeah, there's no way to get asymptotic.
yeah, well,
there are ways.
yeah, there are ways. So the MRRW, what they did is they took the Delsarte P, they compute the dual, and then they produced a symbolic solution for the dual and analyzed and say, aha, this has asymptotics behaving like this. Therefore, now you know the asymptotics, but it was done by hand, not by computer. Right?
I have some that I don't know. So first, just in the definition of the FS,
Yes.
equivalently, there exists an FS such that what?
Oh, for every X and Y, if you want,
Is it to the rates or to R?
oh, it's to relations, not real numbers.
Okay.
Relation.
Okay.
Right, so it's saying, this is just saying,
Now
if you want to determine the relation, all you need to look at is the
now
difference.
it's there.
It factors through the distance, right?
And okay, and
Right, and this is just saying,
FS and FS prime.
so this relies on the fact that they always have a dual. So S prime is the dual, whatever this is. Right? So the dual, oh, and I should say, it always has a dual translation scheme. So this is a fact, which I'm not proving, that if you give me a translation scheme, then this always has a dual scheme, and it's also a translation scheme over X. So if it's also a translation scheme over X, it has a corresponding FS prime, right? Through which the relations factor. So I'm saying that if you want to compute the Qs of your normal scheme, what you do is you take any guy on your scheme that has relation R, right? The FS is R, and you sum over all guys on the dual scheme that have relation S prime, the character, YX.
But doesn't this assume also some uniqueness or something of the dual scheme? Like why is any dual scheme and any F of this dual scheme is fine for that?
No, it needs to be the dual scheme of this, right? So there is a dual scheme and it's unique, quote unquote. I mean, up to permutation. But when I say there's a dual, there's a bijection saying, this should be this dual relation should correspond to this ER matrix on this guy. Now I can also.
It's not completely clear to me why F of the dual scheme is well defined for S.
Okay, I can give you the formal way of finding out what this is. What you do is you say, you take these, remember, you take this formula, right? So this formula, if I forget about this formula is well defined, right? I just take the sum over all code words that on the primal scheme that have relation S, and I do this, right? So now I have a bunch of functions. Each of them is given by a certain X, right? Once I fix X, I have this quantity, right? So what I'm going to do is I'm going to look at the level sets that they define, right? So these functions over X, right? They define some level set, right? And I look at the level sets, and for each S, I have a level set. So I consider all of them and I take the common coarsest partition of them. And that's going to give me the FS prime. That's how you do this on this. So, and then that's uniquely defined. That's how you do it uniquely. But But yeah, you're absolutely right that there's some cheating going on here. Okay. Right. So now the point is.
For which scheme is this? There's the coefficients.
No, so it's going to be just the Fourier coefficients if you're just looking at the multiplication table as Avi suggested.
Okay.
Because then the relations are just
So that's what
But in general, it's not. You're most of the time you're interested when it's not just a multiplication table, because then you won't. If it's just a multiplication table, you're not going to get PNQ functions that are efficiently computable. You really are looking at the whole space. Right? Okay. So why do we care about translation schemes? Well, we care because, if you remember the beginning of the talk, we talked about linear codes as well, right? And then for linear codes, you need to talk about translation schemes. So sometimes they're called linear, sometimes they're called additive, just to remind you that maybe it's not necessarily a field. So what's an additive code? So this is just some subgroup. So it's a code C that is a subgroup. of X. Okay. So these guys are particularly nice because if you want to compute the inner distribution, you can compute it in a much easier way. You can just see all the code words that give you the relation R under this F function, right? So instead of really thinking of the relations being defined as X cross X, you can really think it's defined in a point and it's just doing this, right? You can just do that. And another thing that is nice about linear codes is that you have the notion of dual codes, right? So dual code. So this is just simpler. It's just a point of X such that for every Y in the code. Okay, so this is the dual code. Now, okay. So everyone fine with these definitions? Right. Okay, so you really want
1 or 0.
It's 1 because I'm writing character. Right.
Okay.
I'm writing character, so it's 1. But you're right.
It's -1 to the inner product.
Yes. But this requires sort of it's a field. Let me point out that you really want to think about the dual code as if it was living on the dual scheme, not really in the primal scheme, even though it doesn't matter because it's a subset of X. You really want to think of it as living in the dual scheme, and the reason is because you have what are called MacWilliams identities now. So this MacWilliams identities, what they're going to say is it's the same formula, but you do 1 over C, and you're going to get a C group. This is what this is giving. Okay.
Linear transformation moving the inner distances of the this problem
Inner distribution.
Inner distribution of the code to the inner distribution of the dual.
Of the dual, exactly, except for some normalization factors. I think actually, no, I think it's fine. Yeah. I might have gotten this wrong, but we'll see.
So additive code, is it equivalent to linear code?
Yes, it's equivalent on the Hamming scheme. Well, depends if you know.
Say that your X is the hypercube, the F.
Yes, F2 to the end, it's fine. Then it's going to be equivalent.
Then it's equivalent.
It's not going to be equivalent if the field is a power of prime. But whatever. Because then.
Really?
Yeah, because a subgroup is not the same as a subspace in an FQ, FP squared. FP squared, a subgroup is not the same as a subspace, but okay, right? But yeah. anyways, okay, so we have that. So let's see the MacWilliams identities. And in fact, here's a small disclaimer. I presented this sort of backwards. The MacWilliams identities were discovered first over the binary Hamming scheme, and then the inequalities were discovered, and then it was discovered that actually you just need an association scheme. You don't even need to be working over F2 to the n. I guess in the meantime, they also discovered for the weak Hamming scheme over general fields. Okay, so let's see the MacWilliams identity. Oh, before I see the MacWilliams identities, I need a couple of observations, which is now we're working over translation schemes. So we have actually a Fourier transform, right? We don't have to pretend. Not only do we have these P and Q functions, but we actually have a Fourier transform. So what happens if I have a linear code or an additive code and I do the Fourier transform of it? It's not too hard to see that this is just the indicator of the dual code, but with a certain normalization, which you can also write it, this normalization as well. Okay, this is just you have to check it, but it's true. Okay, so let's prove the MacWilliams identities then. So AC per S is prime. Okay, so there's not much that I can do here. I can just say let's sum overall code words x such that f s prime of x is equal to s prime, indicator of the code of x. Right, so that is just well, not the definition, but the formula that I said there, right? Over the dual.
This S prime, the first S prime is capital.
Yes, yes. So maybe my font is kind of small. Okay, so not much to do here, and you have a hint on the board. You should write this on the Fourier basis. So let's write this on the Fourier basis. Another sum. And then again, we're going to apply the previous hint. You see two sums, just swap them, don't think about it. So, okay, I'm also going to apply this thing here. So we're just going to get 1 C y over C. I don't know where the X. Oh, there's no X. Okay, good. Okay. And now it's nice because now we can use one of these two formulas, which is the top one, because if I knew what X was, what was the relation of X, then I'm just, sorry, if I know what was the relation of Y, then I'm just summing over all characters of a certain dual relation, right? So this gives you well, I guess, yeah, sure. And now that is just this inner sum here is just the distribution of the code, right? So just this, and the C comes out. Okay, so that is the MacWilliams identities. Right. Let me see. Oh, okay. Right. So that gives you a different view over the Hamming scheme, right? You now have this. It's also a translation scheme, which means that it's much easier to compute the P and Q functions. and they're related to somehow a Fourier transform. Now, if you remember the Delsarte, which I think is under here. It is. Okay. But I also think it's in the middle, but maybe not. The point is that if you remember the inequalities, this said that, okay, this quantity was non-negative, right? So of course, if you're working with a linear code, you get that it's non-negative because it corresponds to a count over the dual, right? But how can you explore this, right? If you're going to try to plug this into the Delsarte LP, it's sort of an integrality condition, right? And so it doesn't really help you, right? So the Delsarte LP doesn't really distinguish whether the code is linear or not, right? You don't get anything new.
Well, if you knew it was big, it would give you a better inequality, regardless of integrality. So.
Yes, but then this is also assuming something about the dual code and etc., right?
It doesn't assume much about the dual. You know that at least, for example, one of these inequalities is big, right? Because of the
Yes, sure.
You can,
Sure, you can leverage it a little bit,
integrality.
but it's certainly not immediate, right? You know that one of them is big, but you don't get any simple thing that you can add to the Delsarte LP and say, haha, if I know that the code is linear, then here's an extra restriction that I can put in, right? Okay, so our purpose now is try to see what can we do about this, right? But before we do that, let me do sort of a skeptic route. So if you really care about just analyzing this, you shouldn't care about efficiency, right? You shouldn't care about having an LP that is efficient to compute. And maybe you shouldn't even care about being an LP because the purpose is to try to analyze it by hand. So we could try to just do an approach that is completely from optimization, graph optimization, which is like this. So imagine that, again, I'm still in the setup that I have some D, right, that is contained in R, and say it has the diagonal. What I'm going to do is I'm going to define a graph that is GSD. So the vertex set is just going to be X, and the edge set is going to be the XYs such that, I guess, X, Y is in D. Yes. Maybe I'll write X just for pedantic reasons. Okay, so this is the edge set of the graph. And then you can just see that decodes, is nothing. So a decode is just an independent set. In this graph, right? So you can say, I don't care about all this association scheme stuff. I can just look at this graph and then study the independence number of this graph, right? And if you know a little bit about your graph optimization, you know that the independence number of a graph is always less or equal than the lowest theta function. Of the graph. And in fact, we're going to use a different one. We're going to use what is called the lowest theta prime function, the prime here. And what is this? Well, it's another optimization problem where you do this. Take the maximum of the AM subject to one trace of M to be 1.
M is a set of variables. J is the old one.
Yes. Sorry. J again is 1 transpose. M is going to be the variables. I guess over E. Trace is 1. We're going to say MXY is 0 whenever it's an edge. We're going to say that MXY is always greater or equal than 0 XY. We're going to say that M is positive semi-definite. Okay. So this is not too hard to see that if I give you an independent set, so if A is independent, then 1A transpose over A is feasible. With value.
Is it for any xy in D? The row for any xy in Z in V.
Yeah, the entries are non-negative.
Oh, and because okay.
You want to capture this 1A, 1A, right? It's just basically.
So if you know the Lovász theta function doesn't have this. You don't require the entries to be non-negative. The theta prime, you require the entries to be non-negative. So you could study this. What?
Theta is the maximum number.
Yeah, theta is the optimal value.
Is the optimal value of the J, M.
Yes, exactly. Right.
It's a different relaxation. Now it's not linear.
Yeah, this is now a PSD thing, right? But you could say, well, you know, if I only care about analyzing this symbolically, I don't care about efficiency, right? If you apply this to the Hemming scheme, this is a really bad program because V is exponential in size, and you on top of it you have a PSD condition on top of it, so it's even worse, right? But you know, maybe you don't care. You say, oh, I'm going to analyze this symbolically anyway, so I don't care. I'm going to use this. Maybe this has more power than the Delsarte OP, because after all, this is an SDP, right? So any other questions about this? Okay, so
something not totally related, but is this somehow related to the Corinne-de-Verdier number?
to the what?
Corinne-de-Verdier.
It looks very much like this optimization problem. Of
To what number?
Corinne-de-Verdier. It's the name of a person.
Oh, okay, I don't know.
Okay, it's the
It's related to the Shannon capacity. If it's related to the Shannon capacity of a graph, as I know, the usual Lovász theta. I don't know if the prime is also an upper bound. Okay. So you might be thinking that this program, maybe you have a chance of getting better bounds because it's way harder to run in the computer, but you know it's a SDP program and you're actually looking at the whole space maybe. So maybe you have more chances of getting better bounds. It turns out that no, this is just a different view of the Delsarte LP. So here's the theorem by Schreiber. So in the setup that we're doing up to now, the optimal of the Delsarte LP is exactly the theta prime function of this graph. So I'm not going to actually prove this, but I'm going to just give you what is the direction of the proof. Sort of the idea.
For the proof, what we are saying is that the size of D is the size of a D code is bounded from above by this theta prime G.
Yes, because a D code is just an independent set, right? And this is always an upper bound for the independent set, right? So instead of bounding the codes using this Delsarte LP, a priori you could use this and hope that this is much stronger. After all, you have an SDP in your hands. But it turns out that's not strong. Yeah, it's not. So it turns out that what is actually going on is that the Delsarte LP, it's doing, it's factoring out the symmetries of this problem, essentially. So I'll give you what is sort of the translation. So if you want to prove something like that between two optimization problems, right, that they're optimal matches, there's a standard way of doing this is you take a feasible solution of one, produce a feasible solution of the other of the same value, and vice versa, right? So how do you go from the Delsarte LP to theta prime? Well, you have these ARs, right? And what you're going to produce is you're going to say, well, my matrix is going to be the sum. There's an X here. I'll double check this. Of AR and VR times the matrix AR. Do this, and you get a feasible solution of that. I got it wrong. It's one of this. Okay. So I'll just give a brief reasoning. I'm not actually going to do the computation. If you look at this, right? So if you take a J matrix inner product M, remember that the J matrix, okay, the J matrix is just the sum of all the ARs, right? Because the ARs partition the space, right? So when you do J matrix inner product this, it's going to essentially boil down to the sum of the ARs. You have to consider that, you know, you have a VR here. So that is just accounting for what is the J matrix inner product with each of the ARs. It gives you exactly, I think, VR times X, if I remember correctly. And then it cancels out, and then you get the sum of ARs, which was the objective of the Delsarte LP, which is somewhere there. Now, if you're doing this one, MXY is equal to 0, this is obvious because the ARs also live only inside D, right? So they only live on non-edges. That they're non-negative is also obvious because there is a condition that the ARs are non-negative and these matrices are non-negative. The hard one is to actually prove PST. And to prove PST is you have to change this into the E basis and check that what you get is the Q transform. So that is sort of the intuition. If you do this, you're going to get something slightly weird because you get P's instead of Q's, but you have to use the properties to see that it's just Q's in disguise. Okay, and how do you do the other way around? Well, the other way around, we're going to actually cheat a little bit because instead of saying, you give me a matrix and I'm going to produce a solution here, you actually do a trick and use the duals. So the dual of the Delsarte LP looks like this. I'm not going to actually do the computation, but I'm just going to write it here.
These are the variables.
The B's are the variables, yes. This is the dual of the Delsarte LP. Prime for dual, and the dual of theta prime. Well, prime for dual. I cannot write the dual for theta prime, or it has a prime. The dual for the theta prime is D, such that the identity is N is indefinite, and X Y 1 for every X Y. In V such that XY is not an edge. And the variables here are N. So that's the dual. And the translation from one to the other is you take beta equals to, well, beta you sort of know because this is the objective value, so it should be the objective value. And N is beta I minus position again. Yes. So maybe let's reason a little bit about why this is actually a solution for this. Well, as I said, the objective is obviously matching what was the objective here. Now, if you want to just check that beta I minus N is a positive semi-definite, well, beta I minus N is just this expression without the minus, right? and the B's are non-negative, and these are PSD matrices. So it's obviously PSD. So where are you using this weird stuff? You're actually using to prove that it's greater or equal than 1. So you have to open this up and you have to use it to check that it's greater or equal than 1. Okay. So essentially what this theorem by Shriver is saying is that, the Delsarte LP is just a sort of compressed version of the theta prime function. That's what it's saying, right? It's a more succinct way of representing this theta prime function. Okay.
Can I ask a high level question? I mean, also I'm sure that most of it will be next week, but still what is our objective?
Yes, our objective at this point is to see that there are several different views of a scheme. So you can view the scheme, well, first you have the Delsarte LP, which provides you upper bounds, but there's a different view of the theta prime.
But in the end, we are trying to use it for like an actual analysis of an asymptotic bound.
Yes, that's sort of the idea. So we're not going to actually prove any asymptotic bounds, but I'm going to provide a hierarchy that by a certain level actually finds the correct code value. Right? It's not going to be efficient to run in that level. But the point is that I can give you a slight spoiler for the next one, is that we're going to present this hierarchy in one scheme, but then we're going to say, well, but it's equivalent to the theta prime. And there's another scheme that is also equivalent to this theta prime. And in this other scheme, we can actually prove completeness. So that's why this sort of connection is important, because the hierarchy is actually the one scheme, but the completeness comes from another different representation of the scheme. Well, it's not the scheme, it's a different scheme, but it's equivalent.
So maybe, I don't know if it was clear, but first of all, I asked about the purpose. The Delsarte linear program is not tight. It's a relaxation which is not exact. It just gives an upper bound, which may be far from the truth. And what this hierarchy is talking about that you didn't see here is going to be more complex linear programs, parameterized like the STP hierarchies that you know about, or some of squares or whatever. It's a hierarchy of programs. And some level of the hierarchy, the upper bound becomes tight.
Yeah, so that I did remember. The thing that I still don't see is where are you going and how to be able to do anything that will give you an asymptotic bound out of this field.
Yeah, well, we'll see that. But there's essentially what we're going to do is we're going to take the Hamming scheme and we're going to produce different schemes on top of it that are related to it and that give upper bounds. But it's going to be important that, every time I give you a scheme, you have to think there's always an associated Delsarte LP, which is just the same thing as a theta prime over a certain graph.
If you think that at the end of the next week's lecture, you will know that correct trade-off between rates and distance, you will know. You will not. You will just have a linear program whose optimal solution is that rate.
Yeah, okay, so I guess this is what I was trying to ask.
Nobody knows how to improve the bounds that you wrote in the beginning. The Gilbert.
My question was if our objective is to get this hierarchy of linear programs that give me the optimal solution for a specific size, or is our objective
for any size, for any given n, it will give you the optimal solution.
Yeah, but this is what I meant by a specific size. My question was, are we trying to get an hierarchy of LPs that given an n gives you the optimal thing for this n, or are we trying to develop a method to get an asymptotic bound?
Well, if you get the first, you get the second.
I just want to say, think about what is already known, right? The MRRW bound. It's an asymptotic bound, right?
I don't know how to get it.
Yeah, but you can. I'll tell you.
There's
They have the South LP. The South LP works for it.
Yeah, they take this dual and they produce a feasible solution for this dual with a certain value. And they prove, well, this is a feasible solution and this is the value. Therefore, it's an upper bound.
And they do it for every n. They do it parametric.
Yes.
It's a parametric.
For every sufficiently large n.
Yeah, that's what they do. Yeah. So you can, if you are clever enough, you can maybe get an asymptotic bound.
Yes.
You at least know that in their hierarchy, if you are clever, you will get.
Yeah, or you could even do the opposite. You can say, haha, you cannot do any better than what we know so far, therefore it's already tight, asymptotically at least. We know that the Delsarte LP is not actually tight, but it could be asymptotically tight. The asymptotics that we studied so far could match even though it doesn't match precisely the number.
But you know bounds on how deep in the hierarchy you need to go, or you just know?
Yeah, so we're going to show that by level n you get completeness, and we have sort of a sketch of an argument that says before that you probably won't get it. And when you look at the hierarchy, n is a very natural place because it's when you actually see the whole space, all the information that you think you would need to get completeness.
But it could be that already at log n
Yes.
you're pretty close.
Yeah, pretty close. Yes, pretty close. It can happen.
But you have no, like you don't have anything of that sort, like quantitative.
Well, we did some runs, but it's very small n, so you don't really know if it's reasonable or not.
And is there any way to use the fact that the maximizer in the theta prime is rank? Well, I mean, sorry, the maximizer is not rank 1, but you only need to check rank 1, which is of course not convex. But maybe there is there any way to use the fact that, you know?
So in the completeness argument, we're actually going to show much more than completeness. We're going to show integrality. So partial integrality. We're not going to show that every feasible solution is a convex combination of true solutions, rank 1 solutions, but every optimal one is. That's what we're going to show. So that sort of is the point. Okay. So perhaps, I mean, technically my plan was to talk about Shurian schemes, but I think I'm over time, so maybe I'll leave that to the next time. Yeah.
Right. Just making sure anybody else wants to ask a question.